In example 4, you can see that we have actually three functions, the sine of x, then we have a linear function when we add 2, and then the last one is a logarithm. Remember that when the base is not shown, it's base 10, and I want you to show it if you are doing this kind of exercise, because when you take the derivative, I assure you that you will forget that that's a base 10, and when you take the derivative, you will forget about adding a natural log of 10. So derivative of a logarithmic function of base 10 will be the reciprocal of the inside times natural log of 10. So now, because I'm multiplying by the natural log of 10, something that is a sum, please put parentheses around. And then the chain rule tells me to take the derivative of this, which will be derivative of 2 is 0, and the derivative of sine is cosine of x. So write it in nice and neat. I have cosine of x over 2 plus sine of x, the quantity, times natural log of 10. In example 5, I'm going to show you two different ways of doing it, and the second way will come from the fact that I have the natural log of a quotient, and that can be split up into the difference of the natural log of the dividend and the divisor. So let me just treat this as a natural log of this quotient. So the derivative of natural log is the reciprocal. Remember, if I have natural log of s, and I'm trying to find the derivative of this just simply will be 1 over x. Notice how I'm indicating that I'm taking the derivative of natural log by adding parentheses and putting prime here. I've seen a lot of your work when you just write natural log of x equals 1 over x, and I know what you're trying to say is that the derivative of this is that, but please do not write monstrosities like this. Okay, so the derivative of the natural log is just the reciprocal of the inside, and the reciprocal of the inside, since it's already a fraction, I'm just going to flip it. So I have square root of x minus 2 over x plus 1, and then the chain rule will tell me to take the derivative of the inside. Now the inside happens to be a quotient, so I have to apply quotient rule. So I know that some giant expression is going to come after that. So I'm just going to put brackets. Derivative of the top will be 1 plus 0, which is 1, times the bottom. So I just have square root of x minus 2 minus the top times the derivative of the bottom, which is 1/2 x minus 2 to the negative 1/2. This is awful. Over the bottom square, so square root of x minus 2 square. And so I'm going to try to simplify this. Square root of x minus 2 over x plus 1 times square root of x minus 2 minus, I have here 1/2, let me put it in front, x plus 1, x minus 2 to the negative 1/2 over square root square is just x minus 2. And then you notice how you have two terms inside the bracket, so I'm going to distribute this square root. And it's just because I can see that if I square this, I'm going to get rid of the square root, so that's why it's convenient to distribute the numerator. So let me just leave the denominator out for a while, and I'm just going to distribute the numerator. So I'm going to have x minus 2, the square root square, you will see that it will cancel out, minus 1/2 x plus 1, and then when I'm multiplying this by the entire term, it is convenient for me to multiply it with a factor that has the same base. So this will be x minus 2. Remember that the square root is the exponent 1/2 plus negative 1/2, that will give me 0 over x minus 2. So simplifying some more, I'm gonna have these two cancel out, so I have x minus 2, and then x minus 2 to the 0 is 1, so that goes away. So I have minus 1/2 of x, and I'm gonna distribute, and I have minus 1/2 everything over x minus 2. Now I'm gonna combine like terms, so I have half of x minus half of x, another half of x, and then negative 2 minus 1/2, that will be minus 5/2, because 2 is 4 over 2, negative 4 minus 1, negative 5. Everything over x plus 1, x minus 2. Almost there. I notice that I have 1/2 in common in these two terms, so I'm going to factor it out. 1/2, and then inside I have x minus 5 left, and then over x plus 1, x minus 2. Now the other way to do the same problem, I'm just going to split my natural log. Okay. So I have the natural log of x plus 1 over square root of x minus 2. And this is the same as the difference, natural log of the top minus natural log of the bottom. And then when I take the derivative of an expression like this, then it's just the derivative of this expression, so it's just the difference of the derivatives. So derivative of natural log of x plus 1 would be the reciprocal times the derivative of x plus 1, which is 1, minus derivative of natural log, again the reciprocal, times the derivative of the inside, which will be 1/2 x minus 2 to the negative 1/2. And now I'm going to simplify. The first fraction stays pretty much the same, there's nothing there to be done, but now I'm going to simplify the bottom. So I have x minus 2 to the negative 1/2, and in here this is also equivalent to x minus 2 to the negative 1/2. So when I add those, I'm going to have 1/2 x minus 2 to the negative 1. So you may see the answer like this, or it's equivalent when I don't have negative exponents. This just means reciprocal, so it sends this expression to the bottom, and that's it. In example 7, this is the derivative of this is going to be a lot faster if I apply my natural log properties. And the only thing I just have to be careful is to just remember and to apply the natural log on both sides. Now, why am I interested in applying natural log on both sides? Is because if I do it on the right side, then this just will be, because this is a product, it will be the sum of the natural logs of each minus the natural log of that. So this is a lot faster than applying product rule and then that divided by the quotient rule of both of them. It will take a very long process to do that. So I'm going to apply natural log on both sides. Of y equals natural log of x to 3/4 square root of x squared plus 1 over 3x plus 2. And then I'm going to apply that property where I can split this. So natural log of x to 3/4 plus natural log of square root of x squared plus 1 minus natural log of 3x plus 2 to the 5th power. And now once I do that, then I'm just going to take the derivative of this expression implicitly. So derivative of natural log of y is 1 over y times y prime, and ultimately I'm going to solve for this. And then the derivative here would be the reciprocal, x to the 3/4, and because it's a composition of two functions, it will be times the derivative of x to the 3/4, which is 3/4 x to the 3/4 minus 1, that would be -1/4. Plus derivative of this would be the reciprocal times the derivative of the inside, which is 1/2 of x squared plus 1 to the -1/2 times the derivative of the inside, which is 2x, minus the derivative of this, which is the reciprocal, times the derivative of the inside of the natural log, which is 3x plus 2 to the 4th, times the derivative of the inside, which is 3. Ta-da! Okay, so let's simplify. I had before x divided by x to the -1/4 divided by x to the 3/4, so I'm just writing it as subtraction because they are dividing. Then I had x squared plus 1 to the -1/2, and then I had another one in the denominator, so I'm just subtracting the exponents because they have the same base. And then in here I did 3 times 5, which is 15, and then this is 3x plus 2 to the 4th over 3x plus 2 to the 5th, so that just makes me subtract the exponents. So when I subtract all the exponents, you don't have to show every step, I'm just showing you where it came from. -1/4 minus 3/4 is -1, so that means the reciprocal of x. And here -1/2 minus 1/2 is -1, so that means this factor goes in the denominator. And 4 minus 5 gives me -1 again, which makes me put it in the denominator again. Notice how the -1 only applies to this and it doesn't apply to 15. That's why the 15 stays where it is. In here, this -1 does not apply to the x, so that's why it stays where it is. And the same manner, 3/4 is not affected, so it stays as 3/4. And on the other hand, I had 1 over y times y prime, so that's the same as dividing by y. So because the y is dividing, it goes to the other side of the equal sign, multiplying. And now, because I'm using implicit differentiation, I can't leave it as, you know, y when I know what the y is, so I have to replace it back. This is only possible because I know that my equation is y equals, you know, whatever that is. Not when I had, you know, x squared minus y squared plus 2xy. In that case, I can't replace it because I don't know how much that y is. But in this case, I do know what y equals, so I must replace it back. Okay, for example 8, I'm taking the natural log on both sides because I need to do certain transformation in here. I can't express this function as the composition of two functions. And so applying the natural log is the only way to go in this case. Not like in example 7 where I had the option to you know, do product and quotient rule one after the other. So applying natural log on both sides, it makes me write this exponent as the coefficient of the natural log, and then I'm ready to take the derivative implicitly because in here I just have the product of two functions. Now when I do that, is 1 over y prime, and then the derivative of this product will be f prime g plus fg prime. And then simplifying this, I'm just writing it without a negative exponent. So when I do that, I notice that I can factor out a factor. I can factor out 1 over rad x. And then the y that was dividing here goes over here multiplying, but y is x to the rad x. So I have it over here, and this is my answer. It differs a little bit from the book, but it's because if you do 1 as 2 over 2, then you can have the numerator as 2 plus natural log, then you can have the numerator as 2 plus natural log of x.